Okay, so I don't know if you've noticed, but at the grocery store, if you want to buy shrimp, they are usually sold by the count instead of the weight, right? And so you'll go and you'll see. Well, I mean they're like 1 pound bags, but they don't call them small, medium, and large, right? So you might have a bag and it says 41 to 50 count shrimp. What does that mean? Well, it means in 1 pound of shrimp, there's going to be between 41 and 50 shrimp. They're not all going to be the same size, so you can't tell exactly. So a smaller count means you've got bigger shrimp, right? So those big tiger prawns might be 10 to 15 count because those guys are big, right? And so it only takes 10 to 15 of those to add up to a pound, whereas the smaller ones, it could take up to 50 to make a pound. So we can count shrimp by weighing them. So if you're ever catering for a fancy party or something, and there's going to be 200 people, and you're making hors d'oeuvres, and you need to know how many shrimp to have, this is for you right here. So 2 pounds of 41 to 50 count shrimp is going to have twice that count, right? Because it's 41 to 50 per 1 pound. If we have 2 pounds, then there's going to be 82 to 100 shrimp. We have a similar idea that we use for counting atoms, except we're going to be more precise than 41 to 50. Chemists are often interested in how many particles are in this sample. Why are we interested in that? We are interested in that because chemical reactions occur between particles. When water is formed, it's 2 hydrogen atoms and 1 oxygen atom. And that makes H2O. And so many times we're more concerned with how many particles are there than what mass of those particles there are. So if we want to know the atoms of anything in an ordinary size, anything big enough to see, we're going to count them by weighing them, because in your lifetime you could not count the atoms in a sample of anything that's big enough to see. There's just way too many of them. We use counting units for other things. So a dozen, this is a counting unit. What does a dozen mean? It means 12. Well, 12 what? Well, you said a dozen. A dozen what? A dozen eggs, it's 12 eggs. A dozen chairs, 12 chairs, right? A gross. Ew. A gross is 144, which is a dozen. These are good English units, right? There's another one that you might have seen. Probably haven't seen gross. 1 ream. A ream is 500 sheets of paper. It's a big number. Those counting units are too small for the ginormous numbers that we're counting. So we have our own counting unit. We sometimes call it the chemist's dozen, because everybody understands what a dozen is, but it can be hard to get your mind around what this thing means. A mole, M-O-L-E, it's not mole, it's not a little blind animal, it's mole. And silly little unit with 4 letters, it has a 3-letter abbreviation. So a mole is the amount of material that has this many particles in it. 6.02214 times 10 to the 23rd particles. That's a heck of a lot of particles. So we can say that 1 mole equals this many particles. This number has a name. It's called Avogadro's number, after the guy whose work led to us knowing what this number is. Yeah?
Now, is Avogadro's number exact?
No. Avogadro's number is not exact. We do know more digits than this, but most of the time we're just going to use 4 sig figs, 6.022 times 10 to the 23rd, because all of our other numbers have 3 or 4 sig figs, and so there's no point in using all of those extra digits if we don't need them. But no, it's not an exact number. Is Avogadro's number like pi, meaning it doesn't repeat itself? Well, I think you could say there are actually lots of numbers that would continue forever. Would it continue forever without repeating itself? I don't know. My guess is not. I don't know if anyone's tried to figure that one out. Yeah, pi is weird. So 1 mole of anything is 6.022 times 10 to the 23rd units of that thing. Those units could be atoms, they could be molecules, whatever the particles are that make up that substance. So here's a picture of 1 mole of copper atoms, 22 pennies. You could hold those in your hand. It's kind of a nice amount. It's big enough to see, but you don't need a cart or something to carry it around. A tablespoon of water is close to 1 mole of water molecules. So a mole of something is a nice amount that you can hold in your hand, right? But mole counts the particles. How did we come up with this number? So the mole was defined so that it is equal to the number of atoms in exactly 12 grams of pure carbon-12. Does that definition sound like the definition of another unit that we learned recently? An atomic mass unit? The atomic mass unit is equal to 1/12 the mass of a carbon-12 atom. So this is talking about 12 grams of pure carbon-12. However many particles are in that is the mole. So 12 grams of carbon is equal to 1 mole of carbon atoms. The mole gives us the relationship between the mass of something and the number of atoms. And so we can count the atoms just by weighing them. Just like you could count shrimp by weighing them. Yes?
Is there any reason why it's a carbon-12 atom, or is it just kind of like they picked it?
That's a great question. Why carbon-12? I believe it was because carbon-12 is extremely stable, it's not very reactive, and it's plentiful. Easy to get a hold of. There's carbon-12 everywhere. Yeah, I think that's why. So we need to know how to convert between a number of moles of stuff and the number of atoms in that. And it is very much like converting between dozens of eggs and number of eggs. So 1 dozen eggs is equal to 12 eggs. For atoms, we're going to use 1 mole of atoms, that's the chemist's dozen, is equal to Avogadro's number of atoms. And this number is one of the reasons we have to be able to use scientific notation on our calculators, because it won't fit in decimal notation. So we can take this unit equation and make 2 different conversion factors. 1 mole of atoms per 6.022 times 10 to the 23rd atoms, or turn this upside down. Remember, in a conversion factor, the thing on the top is equal to the thing on the bottom. A pure silver ring contains 2.80 times 10 to the 22 silver atoms. How many moles of silver atoms does it contain? We're going to do a problem like this using dimensional analysis. So I read the problem, and then we're going to highlight the numbers. There's actually only the 1 number in there. And then we're going to highlight what it's asking us to find. How many moles of silver? So then we're going to map out what we're going to do so we don't get lost. There's only one number, so that's going to be our starting number, 2.80 times 10 to the 22 atoms. And then what are we trying to find? We're trying to find moles. And then we need to figure out how can we get from atoms to moles. Well, that's what we just learned about. The definition of a mole, or the value of a mole. So we're talking about atoms here. A mole is 6.022 times 10 to the 23rd atoms. A dozen atoms is 12 atoms. It's just that's not useful here. So this is the relationship between moles and atoms, and so we can just do this in one step. We can go straight from atoms to moles. So we write down our starting number again with the unit. We look at the path that we laid out. It has one arrow, so we're going to have one conversion factor. Then we look at the units in this path, atoms to moles, and those are the units that are going to be in the numerator of any fractions that we have, so atoms to moles. We want atoms as a unit to get canceled out, and so we're going to put that unit down here. We'll be dividing by atoms, so the atoms cancel out. We put all the units in, and then we do the numbers. If you don't have this firmly in your head yet, write it down and look at it. 1 mole is this number of atoms. Sometimes students get it backward and say that 1 atom is Avogadro's number of moles. So you're telling me that 1 egg is a dozen eggs. Is 12 eggs. No, not correct. So 1 mole, Avogadro's number, here we're dividing by a number in scientific notation. You need to be careful with your calculator. So if you have your calculator with you, please get it out and make sure that you know how to communicate with it. You should be using the scientific notation button, EE or EXP. And if you're not sure where that is, I'll be happy to come and show it to you. So we've got 2.80 EE. It's only showing me 1 E in the display, that's fine. And then I'm going to press the 22. When you press that EE button, think times 10 to the. And then I'm going to divide by 6.022, pressing the E button, times 10 to the 23, and press the equals button. Did you get that number? If you get a really, really big number, sorry, YouTube people, I accidentally paused it at some point, and so here we are. How many sig figs should this answer have? 3. Our starting number has 3. This is not an exact number, but it has 4. And so this should have 3. I'm going to be talking about sig figs the whole semester, because getting close to the right number of significant figures is important. Getting it exactly right every time at this level, it's not that big of a deal. But we don't need to write out all these digits, because these are actually pretty meaningless. So this is 3 sig figs. Now, a problem I've noticed is some students are not rounding up when they should round up. So this is the number we're getting rid of. We have to look at the next digit. Is it 5 or greater? Well, this is 9. That means that this is closer to 5 than to 4. And so I'm going to round up and call it 0.465 moles. Yes, you could also say this is 4.65 times 10 to the negative 2. Mm-hmm.
If the squares were the same, like 10, if it was 10 instead of 22 and then 10 to 22, I can cancel those out, correct?
You could, yes. Yeah, some of you are great with exponents and you recognize that, oh, well, I can take 22 minus 23 and I can take this divided by that and put them together, but then you're still going to have to do a little wiggling. So unless you're like, well, of course I can do that, don't even think about it. Any other questions?
You read it down, do you want to put like, 0.0465 like AG moles, like silver moles, or is it just right?
That's a great question. Should we say that it's moles of silver or not? Right now, it doesn't matter, right? Because this problem is only talking about silver. Later on, when we talk about chemical reactions, it will become important to write down moles of what. And so it would be best to say moles of silver. Great question. Anybody else? There's the answer. So we can find out how many moles there are by weighing something. But if we want to actually be counting, find out the number of atoms, we need one more conversion factor. We need to know the mass of a mole of atoms. So this is like the count of the shrimp, right? We need to know how many grams this particular number of things is. So the mass of 1 mole of atoms is called the molar mass. So molar mass, mass of a mole. Atomic mass, mass of an atom. When we're talking about atoms, they're teeny, teeny, tiny, and so we use a teeny, teeny, tiny unit, atomic mass unit. When we're talking about the mass of a mole, this is big enough that you can see it and hold it in your hand, and so the unit now is grams. This seems magical, but it was actually done on purpose. An element's molar mass in grams per mole is numerically equal to the element's atomic mass in atomic mass units. And that's because of how the atomic mass unit and the mole were designed. So it makes things really convenient. So if we're talking about a mole of aluminum, mole of carbon, mole of helium, they're going to have different masses, but they're all going to have the same number of atoms. Aluminum is going to weigh a lot more than helium because the particles are a lot bigger and each of the particles weighs more. So we're going to use molar masses a lot. The molar mass of an element is the conversion factor between the mass in grams and the amount of moles. So for carbon, carbon-12 is exactly 12 atomic mass units, but the average carbon atom is 12.01 grams per mole. So if we look at carbon on the periodic table, we see this number. So 12.01 grams of carbon is equal to 1 mole of carbon, and we can make 2 conversion factors from that. Let's calculate the amount of copper in moles in a 35.8 gram pure copper sheet. So highlight the numbers, highlight what we want to find, amount in moles. .8 grams. Come let's be thorough and say it's grams of copper. And we want to find out how many moles of copper that is. What's the path? We can do this in one step using the molar mass, because the molar mass is the mass of a mole of copper. So 1 mole of copper, its molar mass is on the periodic table. So under Cu, it says 63.546. So 63.546 grams of copper is equal to 1 mole of copper. We can go directly from grams to moles. So we'll take our mass in grams. We have 1 arrow, so we have just the 1 conversion factor. Grams to moles. So here we're going to have grams to moles. And we need the grams to cancel out, so we stick those down here. And this is the units telling us which conversion factor to use. Should we use 63 grams per mole or 1 mole per 63 grams? We let the units tell us which one. So I need moles on the top and grams on the bottom. It's always 1 mole and a number of grams. So we've got 1 mole, and then here we've got 63.546 grams. And that's it. So 35.8 divided by 63.546. And as usual, my calculator is showing me a lot of digits, and I don't feel like writing them all down anymore. So before I finish that, I'm going to look at what I started with here, 3 sig figs. Is this molar mass an exact number? No, it's not. It's measured. So that has 5 sig figs. So 3 is smallest, so this answer should have 3 significant figures. So I'm going to keep 3 sig figs and just write down the 2 next digits. And then I'm going to round that, and I'm looking at this digit here. It's less than 5, meaning this number is closer to 3 than 4. And so it's 0. Gosh, what did I do? I don't know what I did. It's reminding me that we have lab today. How could I forget? 563 moles of copper. Questions? Is anybody curious why we were talking about 12.01 grams per mole for carbon, but up there on the wall it says 12.0108? So some periodic tables are going to give you more significant figures on the molar masses than others. The one I'm going to give you for exams just has 4 sig figs for all of the atomic masses, the molar masses. Because for our calculations, that's enough, right? If you're doing something that's more precise, you maybe need more digits. Some of those have 6. And I'm sure some of them are known to more digits than that. There's just not really enough room on the periodic table. We don't want the molar mass to reduce the number of significant figures in an answer. Sometimes students are tempted to round them. And they want to call 63.546, they want to call that 64. That's a really bad idea. So I want you to use 4 sig figs in your molar masses. You can use more if you want, but 4 sig figs in your molar masses, okay? So this is the conceptual plan for how to count atoms by weighing them. So we need to know the mass of the sample. We can convert the mass into moles. That's using the element's molar mass. And then we can convert the moles to number of atoms using Avogadro's number. So this is the plan here, the path. The grams to moles to number. You notice moles is in the middle of this. We'll be doing a lot of calculations where you've got some unit over here and some unit over here, and there's something missing in the middle. In chemistry, mole is in the middle a lot. I didn't watch it, but there was a TV show called Malcolm in the Middle, right? This is moles in the middle. You almost always find moles in the middle. So if you don't know what unit to go to, try moles, okay? How many carbon atoms are there in a 1.3 carat diamond? Diamonds are a form of pure carbon. 1 carat equals 0.20 grams. Okay, this one is a little more interesting or confusing depending on your point of view. So let's highlight the numbers. We've got 1.3 carats, and we're told that 1 carat is 0.20 grams. And then what do we want to find? Carbon atoms. How many carbon atoms? It's hard to get somewhere if you don't know where you're going. Because even if you get there, you won't know that you've gotten there, right? And it's not a good idea. We want to know where we're starting and where we're going to go. So I've got 2 numbers here, and so my strategy is I'm going to write both of them down, because up there in the problem, they're kind of, jumbled up in all those words. So let's just pull them out. One of those is our starting number. What are we trying to find? We're trying to find atoms. One of these could be a conversion factor because it relates to different units. Which one is that? This one, right? 1 carat is 0.20 grams. So I'm not going to start with that one. They gave me that for a reason. That's a conversion factor I'm going to need, and it's one that's tricky to look up because we don't use carats much in chemistry. So this is what I'm going to start with. So that's my starting thing. And this is my ending thing. Right? So now we have to figure out how to get from carats to atoms.
So, okay, so would you do 1.3 carat, use that conversion factor from 1 carat is 20 grams, and then do grams to moles and moles to atoms?
Exactly. Yep. So let's keep numbers out of it for now. From carats, I can go to grams. Ooh, that was scary. Where did it go? I hate it when that happens. Phew. Okay. This relates carats and grams. So we can go from carats to grams. And then going from grams to atoms, there's a unit in the middle that's missing. Maybe it's moles, right? So let's write moles in here. And then we can't just throw moles in everywhere. We have to make sure, can we convert from grams to moles? Yeah, we just learned how to do that tonight. This is a diamond, but diamonds are carbon. And so the periodic table is going to tell me how many grams of carbon are in a mole. Can I convert from moles to atoms? Yeah, that's Avogadro's number. Okay? Unless you're whipping through these problems and getting the right answers, please write this path out. It really does make it easier. Okay, 1.3 carats, and I'm just going to count the arrows, 1, 2, 3, and I'm gonna make an equal number of conversion factors. 3 arrows, I'm gonna have 3 fractions. I'm gonna take my path, carats to grams to moles to atoms. I still hear Dora in my head. Dora, Dora, Dora the Explorer. She's super cool, Explorer Dora. Sorry. Carats to grams to moles. I was thinking the other day, I need to find a clip from that show to show in class. These are just the units I figured out, right? I'm just gonna write them down here. And then I take the first unit and I divide by it in the second one because I need it to go away. I want those to cancel out. I'm gonna put gram down here because I want the grams to cancel out. I'm gonna put the moles down here because I want them to cancel out. All the units in there canceled out, really, and then I'm gonna put the numbers in. Well, this guy relates carats and grams, and this is the fraction that has carats and grams in it. It says 1 carat, so 1 carat and 0.20 grams. Then I need this relationship between grams and moles. That's where the periodic table comes in. So if we look on the periodic table, this one says 12.0108. 12.10108 grams of carbon is equal to 1 mole of carbon. So 1 mole, 12.10108 grams, write that in there. Moles and atoms. Moles are the chemist's dozen. A dozen atoms is 12 atoms. A mole of atoms is that weird number. Mm-hmm.
The yellow periodic table elements that we got has mass flow, it's 12.011.
Yes, thank you. Because I transposed digits. This one says 12.01, and I wrote 12.10. I didn't transpose digits. I put an extra digit in there. Get out of there. And then, that's not that. We'll do this. And then I'll just scoot that guy over, and we can pretend that didn't happen. It didn't work. Come on. Oh, I know what happened. Never mind. Okay. Fine. Be that way. Thank you for catching that. So Avogadro's number of atoms is 1 mole. So 1 on the bottom. Thank you. See, I need you guys. What would I do without you? There we go. Okay. You're doing a worksheet problem, and you wrote all this stuff out, and you calculate it, and you type it into the quiz, and it says it's wrong. It happens a lot. What do? Well, when you've got lots of stuff going on like that, one of the first things you want to do is look and make sure that all the numbers are correct, right? Because sometimes people might lose this decimal point and have 13 carats. Or do what I did and just for no reason, stick an extra 1 in there, right? So go check the numbers. If they're all correct, then do the calculation a second time. So I'm not doing calculations a second time here because I have you to catch my mistakes. So let's do this together. And again, I'm getting a big mess of numbers. How many sig figs? Only 2. So 1.3, I'm just going to write down the next two digits, if it will let me, and then times 10 to the 22. Now, on your calculator, there's a whole bunch of digits. You know, mine just looks like 1.30359343E22. It can be easy to overlook the E22 on the end and write down 1.3. Because a 1.3 carat dime is pretty big. And we're saying it has 1.3 atoms in it? That's messed up, right? Well, make sure you look all the way to the end of the number, and it's times 10 to the 22. So then I can round this 1.3 times 10 to the 22 atoms of carbon.
So does like carat have a singular symbol, just carat?
That's a great question. Does carat have a symbol, an abbreviation? I'm sure it does, but I'm not a jeweler, and so I don't know. Yeah, great question. Any other questions? Okay, so we were talking about how small atoms are and how teeny tiny electrons are, right? Now we're going to talk how big something is. So, how big is Avogadro's number? Avogadro's number of pennies would cover the Earth's entire surface to a depth of 300 meters. That's 3 football fields. That's a lot of pennies. Avogadro's number of grains of sand would cover the state of Texas to a depth of several feet. If you counted 24 hours a day for the rest of your life, you didn't stop for anything, you couldn't count to Avogadro's number. And this is what it looks like in decimal notation, right? Such a mess. So we can do some other problems using Avogadro's number. A titanium cube contains 2.86 times 10 to the 23rd atoms. What is the edge length of the cube? The density of titanium is 4.50 grams per cubic centimeter. This might be giving you flashbacks to the Antarctica problem, or that cylinder with the pesky length, height, whatever it was. I'm going to highlight the numbers, and then I'm going to highlight what I'm supposed to find. The edge length of the cube. Okay, well, we're going to write down the numbers. 2.86 times 10 to the 23rd atoms, and 4.50 grams. There's a slash there because it's easier to type. You're not typing now, you're using your hand. It's a vertical fraction so that you recognize it as a fraction. Grams per cubic centimeter. And I'm trying to find edge length. They didn't tell me what unit. Well, is there a length unit hiding in either of these? Centimeters. The centimeters cubed gives us a volume. So centimeters would probably be the easiest unit to go to. If it tells you meters or miles or something, then you have to do that. But if it doesn't tell you, you can pick whatever's easy. So how do we get from atoms to centimeters?
So we could do atoms and Avogadro's number, and find the mass from
From grams?
and then do centimeters.
Yeah, so there's that mole in the middle again. We could take the number of atoms, convert them to moles, and then find the mass. And then we can get to not the edge length, but the volume, right? We can get to cubic centimeters using the density, but we can't do this with dimensional analysis. Sometimes there's an equation that you have to use. Sometimes it helps to draw a picture. There's my cube. If I call the edge length L, the volume is equal to L cubed. So if I find the volume in cubic centimeters, I can use this equation to find the edge length. So this involves a skill called critical thinking. In Chem 3A, we give you problems on exams that we showed you specifically how to do in lecture. You may not remember that we showed you, or you may not recognize that it's something we showed you, but we do. In Chem 1A, on the exams, I guarantee you there will be a problem that is unlike anything you saw in the homework or in lecture. It involves the same pieces that we taught you, but you have to put them together in a new way. That's critical thinking, and it's part of the class. So doing a problem like this helps you to get better at critical thinking. Okay, so we're going to do dimensional analysis to find the volume. So 2.86 times 10 to the 23rd atoms. And I've got three arrows, so 3 fractions. Atoms to moles to grams to cubic centimeters. Atoms down here, moles down there, grams down there, and those units are going to cancel out. Then I'm going to look at each of these moles and atoms. Well, that's the Avogadro's number. 1 mole is Avogadro's number, and a lot of times there's not enough space for it. Grams to moles, where do we get that from? Periodic table. What's the element symbol for titanium? Ti. A good guess is the first 2 letters. So Ti, make sure that you don't mix it up with TL. That L looks like an I a little bit. 47.867. 1 mole, 46.867 grams. And then this one, here's our density. 4.50 grams. It goes down here per 1 centimeter squared. Cubed. 2.86 EE23 divided by 6.022 EE23 times 46.867 divided by 4.5. How many sig figs are we going to need? 3. This number had 3 and the density had 3. Densities are not exact. So 3, but I'm going to write down the next 2, and that's that many cubic centimeters. I'm not going to round it yet because I'm not done. How do we rearrange this equation to get L by itself? We have to undo the cube root. Undoing a square is the square root, undoing the cube is the cube root. So L is going to equal the cube root of the volume. So let's write that down, and then we'll talk about how to put that on your calculator. We won't do cube roots very much. Yes? Is it 47? And I wrote 46? Is that the problem?
Yeah,
I was just testing you.
it's
Wish. Okay. So that messes up my number.
Just the five. It's
5.05?
5.05. Yeah, 5.0510.
5.0510. Thank you. Okay. So some calculators have a button that allow you to do roots other than square root. The TI-36X Pro has a button like that. It looks like the square root symbol, but it's got a little box by it. And so to use that, you're going to press the kind of root you want, here 3 for cube root, and then I'm going to press that button, and then I'm going to type in my value, which is 5.0510, and press equals, which is going to give me 1.7157, which would round to 1.78 centimeters. No, it wouldn't. Good grief. What am I on? Pardon me? So if you don't have that special button, or you don't know where it is or how to use it, if you raise the number to the 1/3 power, it will give you the cube root. And don't worry, this is not something I'm going to do to you on an exam. So you could take 5.0510 raised to the 1/3 power, and that'll give you the cube root. Any questions? Phew, got it right. Oh, good heavens. My question was, when are we going to get to the end of this chapter? There it is. There's the end. Yay!